Hello. What I'm planning to do today is show you a little bit about a map that I draw for my kids to show plate tectonics, rocks, maybe a little meteorology, astronomy, lots of things. But basically, I have them draw a mountain range on this side, down to a coast, ocean floor, flat-bottomed ocean floor, more or less flat-bottomed, to a deep trench, up to another mountain range, looks something like this. Go in and throw in some water, waves, like this, maybe even a cloud or two. And then we could throw a sun in there. We can throw some beams. It'll rain. A couple birds in the sky. And then let's get back down to the issue. Okay, so what we start off is with Continental Rock. You can also call it granitic rock. Has an average density of about 2.7 grams per cubic centimeter. Made up of granitic rock, which tends to be very felsic. Means higher in silica, makes it less dense, which is why these continents float up above the ocean floor, which would look something like this. Okay, and then we have oceanic rock. Okay, oceanic rock or instead of granitic rock, basaltic. Has an average density of about 3.0 grams per cubic centimeter, and is made out of incredibly mafic rock. And then down here we have the mantle, upper mantle, but we'll call it mantle just the same, made of ultramafic molten rock. Have an average density of about 3.3 to 3.5 grams per cubic centimeter. So we have oceanic floor floating on this. We have felsic continental crust floating on this. And then I have them erase the middle part, make this a little bigger, erase the middle part of this ocean floor. In fact, I'm going to erase more of it because I don't like how thick I drew it. Go back into the pen. Make one of those. I hate it when these things are in the same place. I want a size 2 brush. Go back into white. Okay, and what we're going to do, actually let's do red first. What we're going to do, actually let's do white, yellow. We have incredibly hot rock down here. Hot rock tends to heat up the air around it, which makes things less dense, which makes things rise. And when they rise, they go up like this. When they hit this ocean floor, which let's say looks like this, it actually hits this ocean floor, pushes it up, and then the ocean floor ends up looking, I don't know why it's erasing so lightly, because I have 30% flow, that's what it is. And then we actually end up with ocean floor that gets pushed up. Still erasing. Ocean floor that gets pushed up. I don't know why it keeps flipping. Ocean floor that gets pushed up, and it looks something like this. And we actually call this the mid-ocean ridge. Mid-ocean ridge is an area of divergent forces. Divergency. Divergent means that the crust is being pulled apart. And if I was going to draw the molten rock rises, and some of it goes off this way, some of it goes off this way, then it actually moves over, it cools, takes a dip down, does the same thing this way, and eventually works its way back around to get heated. This stuff flows very slowly. These guys are called convection cells. Looks a little weird right there, but convection, V-E-C-T-I-O-N, cell. Same thing over here, convection cell. These convection cells push these crustal plates made out of the crustal rock, as well as the upper part of the mantle. So the mantle moves, the crustal plates move. This is divergent MOR. It's also called a spreading center. Because that's an area where things spread. If I was going to show you a picture of the ocean floor, it would look like this. These sections right here are actually the mid-ocean ridge. The mid-ocean ridge, you can see, is actually a 46,000 mile long mountain range. It's this black line that you see going around the globe. It actually does have some places where it sticks up out of the water, like Iceland, but for most of the whole entire range, it's underground. It's underwater, excuse me. Again, 46,000 miles long. Okay, so this is just a cross section of it. This mid-ocean ridge, if I go back, this picture is actually showing you the age of the rock. It talks about 0 being the dark line and the very dark red, and as the red gets lighter and lighter to orange, finally to yellow, to light green, to green, the light blue to blue, gets older, and we're talking about 180 million years. So look on both sides. The age of the rock changes about the same rate, and I can do that on here also. If I pick a color that I haven't used yet, this is like 0 million year old rock, and if you move over a little bit, this is like 10 million year old rock, and if you move over here, this is like 50 million year old rock. And all this means is 50 million years ago this rock was sitting at this mid-ocean ridge. And if you go all the way over here and say this is about 200 million years old, and down here about 200 million years old, it's the oldest rock in an ocean. What this basically means, if this was the United States of America, and this was Europe, could be France, could be any place, 200 million years ago, North America was here. Europe and Africa were here, and it started splitting apart, and the Atlantic Ocean has been moving basically this direction ever since. Okay, so let's get down to this area. This area, if I pick the same color, this is called a DOT, which stands for Deep Ocean Trench. And if I go back to here, the deep ocean trenches are these dark areas that you see. And if you actually throw this whole thing in, this is why it's called the Ring of Fire. Volcanoes going off over here, San Andreas Fault, Baja California, and all the way up to the San Francisco Bay, which you saw in another video that I posted, is actually moving up here towards this Aleutian Trench. If you notice, these things are very arc-shaped. This is where we talked about volcanic arcs or island arcs. depending if we, again on that same video where we talk about the plate boundaries, or where I talk about plate boundaries. But if we go back to here, that's the deep ocean trench. Instead of divergent, this is an area of convergent forces. And instead of a spreading center, this is called a, I'll write it down here because it's a little easier to see. This is a subduction, what basically means forced under zone. Okay, and I have this diagram drawn a little incorrectly, so I'm going to give a little bit more space, and I'm going to draw it more like this. So there's the Continental Rock. Which again is the granitic rock in 2.7 grams per cubic centimeter. This is the Oceanic Rock, again at 3.0 grams per cubic centimeter. And when these two plates run into each other, when this plate moves this way, when it runs into each other, this is the plate, because it's more dense, that gets forced down, subducted. As it gets forced down, we get runoff coming this direction, so we get material that actually ends up down in this trench, deep ocean trench, and water gets pushed down. So we get this continental rock, and we get this water pushed down, and as this rock gets pushed down, subducted down, it actually warms up and it starts to melt, and this melted rock becomes more buoyant, and some of these blob up to make magma chambers, which can solidify to make igneous rock internally, which we would call a batholith, a massive discordant body, or it could form a laccolith, which is a massive concordant body, or some of these may actually go all the way up and make magma chambers up here, which can go up and eventually make volcanoes, which can erupt. We go to Bowen's reaction series, which looks something like this. The hot end, the cool end, the mafic end, where we have the discontinuous series with olivine all the way down to biotite mica, and the continuous series where we talk about the plagioclase, all from going calcium down to sodium, and then we actually have the felsic stuff, the thick viscous, versus the mafic, the thin runny material, much down here in the cooler range, where we actually have biotite mica, muscovite mica, and then another type of feldspar. This is K-feldspar, and then we actually have quartz. So these are the mafic minerals that make up, the felsic minerals that make up the continental rock, and these are the mafic minerals that make up the oceanic rock. Partial heating. If I was going to actually make felsic purple and mafic, mafic as in yellow, what happens is if this rises very quickly, the yellow material goes all the way up, and it can go even farther up, making these magma chambers that are up here. If it actually goes up slower, the mafic material, as it cools, solidifies and stays down at the bottom of this magma chamber, which tends to make this magma more felsic as it moves up. Felsic being thick, cooler temperatures making it thick, and water vapor, with the water going in, actually does make it thinner, but it can make these things intermediate and very violent in eruptions, like Mount St. Helens, Mount Rainier, Mount Baker, Mount Mazanoff, which actually makes Crater Lake. This is all created in something, I need a different color. This is all created in something, I don't know if this is going to show up, in what's called an active continental margin. And this one over here, we don't get volcanism, we don't get earthquakes, we don't get new rock, we don't get volcanoes, we don't get anything like that. This is a what's called a passive continental margin. And this is the east coast of the United States, Virginia, where I live. We also have a passive on the other side. This is not really the Atlantic Ocean, even though it sort of shows all that. I think I've got everything in here that I want to put on this diagram. If not, let me know. Okay, thank you much.